In this example, we're going to find the derivative of f of x equals square root of x using the limit definition. So remember that the limit definition of derivative, f prime of x, is equal to the limit as delta x tends to 0 of f of x plus delta x minus f of x all over delta x. Alright, so what does each of these things mean? We have three parts. We have f of x plus delta x, we have f of x, we have delta x. So this part is telling us to substitute x plus delta x in for each x in the original function. And this is just the original function. And then that's all over delta x. Now if you substitute in 0 for delta x at this stage, you're going to get 0 over 0. What we need to do is multiply by the conjugate to rationalize the numerator. The conjugate of what, you might be asking? The conjugate of this numerator. Actually, we're going to be multiplying by that conjugate divided by itself, so that we're actually multiplying by 1. Alright, so we'll have the square root of x plus delta x plus the square root of x. Remember that with the conjugate, you change the operation between the two terms. And then you'll multiply by the same expression in the denominator, so that we are multiplying the entire fraction by 1. So let's multiply the numerators together. If you multiply root x plus delta x by root x plus delta x, you're going to get x plus delta x, just from the definition of square root. Now if you multiply the outer terms together, you're going to get the square root of x times the square root of x plus delta x. If you multiply the inner terms together, this one and this one, you're going to get minus the square root of x times the square root of x plus delta x, which is convenient since they'll add up to 0, and that's exactly why we chose to multiply by the conjugate in the first place, because of that adding up to 0. And then we'll have minus x. That's all over delta x times root x plus delta x plus root x. I'm not going to multiply that out since it's already factored, and we're going to want everything factored so that we can simplify in just a moment. Alright, so does anything go away? Well, this part and this part add up to 0. And then the x minus x, that'll add up to 0, and I believe we're going to be left with just delta x in the numerator. We'll have a delta x times root x plus delta x plus root x in the denominator. Those will go away in our simplifying. At this stage, we should be able to safely substitute in 0 for delta x. And when we do that, we'll get 1 over root x plus root x, which is 1 over 2 root x. Here we are asked to find the derivative of f of x equals x squared minus 2x using the limit definition of derivative. Recall that that is the limit as delta x tends to 0 of f of x plus delta x minus f of x over delta x. So this is telling us to substitute in an x plus delta x everywhere we see an x in the original function. So that'll be x plus delta x squared minus 2 times x plus delta x. Then we subtract off x squared minus 2x. That's the function we were given. And if we substitute in 0 for delta x at this point, we'll get 0 over 0, which isn't good enough. So let's multiply all this out and combine everything we can, and then we should be able to simplify and get a more meaningful answer. All right, so remember that what this is telling us to do is to multiply x plus delta x by itself. So when we do that, we should get x squared plus x delta x plus x delta x. That's 2x delta x plus delta x squared. Remember that delta x is a single variable. It's just a variable that has a two-letter name. Now we have minus 2x minus 2 delta x minus x squared plus 2x. And then that's all over delta x. Now a lot of this is going to combine. The x squareds are going to go away, the 2x's are going to go away, and what we are left with will be much easier to work with. So we've got 2x delta x plus delta x squared minus 2 delta x over delta x. And again, if we were to substitute in 0 for each delta x, we would still get 0 over 0, meaning we're not finished. However, we can factor out a common factor of delta x in the numerator, and that'll leave behind a 2x plus delta x minus 2. And that's going to go very well with the delta x in the denominator. So that's going to leave us the limit as delta x tends to 0 of 2x plus delta x minus 2. At this stage, we can safely substitute in 0 for delta x, and we'll get 2x minus 2. In 7a, we are asked to find all vertical asymptotes of the function x squared plus 5x over x squared minus 25. Well, the numerator is a continuous function, it's continuous everywhere, and the denominator is continuous everywhere. The values of x that are going to give us vertical asymptotes are the ones that make the numerator 0. I'm sorry, let me change that. Values of x that make the denominator 0 and the numerator not 0. So let's look for values that make the denominator 0. Set the denominator equal to 0. That'll solve pretty quickly. X squared minus 25 equals 0, x squared equals 25, x equals plus or minus 5. Now, is either one of those going to give us a 0 in the, or I guess what we're looking for is non-zero in the numerator. So if we substitute in 5, we get 25 plus 25 is 50. So x equals 5 gives us something that looks like this, 50 over 0. The numerator will be 50, the denominator will be 0. We have a vertical asymptote there. What about at negative 5? Well, if we substitute in negative 5, we're still going to get 0 in the denominator, but the numerator will also be 0. It'll be 25 plus a negative 25. So no vertical asymptote there. So x equals 5 is the sole vertical asymptote. In 7b, we are asked to find all the vertical asymptotes of x over sine x. So we look for all the places where the denominator is 0. So when is sine of x equal to 0? Well, that would be at 0, pi, 2 pi, 3 pi, and so on. Also, negative pi, negative 2 pi, actually at any integer times pi. Now, if we substitute in negative 2 pi for x, we would get negative 2 pi over sine of negative 2 pi, which would be negative 2 pi over 0. We'd have a vertical asymptote there, since these are each continuous everywhere. In fact, if we substitute in any of these non-zero values for x, so pi, 2 pi, 3 pi, and so on, negative pi, negative 2 pi, negative 3 pi, and so on, we're going to get a non-zero numerator and a zero denominator, and we'll have a vertical asymptote. But what about when x equals 0? Well, when x equals 0, we get 0 over sine 0. That's going to give us 0 over 0. And you may remember the limit as x tends to 0 of sine x over x is 1. Well, this is just the reciprocal. And so that tells us that the limit as x tends to 0 of x over sine x is equal to 1 over 1, which is 1 as well. So you don't have a vertical asymptote here. In order to have a vertical asymptote, at least one limit from one side, at least one one-sided limit is going to have to be either infinity or negative infinity. And we're not going to have that. We've got a function that's headed toward 1. I don't know what it does out here. Probably all kinds of crazy things. But there's no vertical asymptote there. So where are these vertical asymptotes? I think I'll just write it this way. Plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, and so on.